restart, then my remote control works. I mean, it happens a lot. Yeah. All right. Yeah. Recursive thinking. Yeah. I think all of you should have some experience about recursive algorithms. Yeah. All right. Now let's learn some underlying theory about recursive thinking. Why recursive thinking is important in problem solving. Yeah. Actually, from what we have learned in Module 1, Module 2, we have learned some experience related to recursive thinking. I mean, there is some connection. Yeah, connection. Remember, bridge the gap way, right? We solve a problem relatively easy at first. After that, then we go to more general case, then we bridge the gap. This idea is exactly the recursive thinking way. Recursive way. Yeah, so you will see that. All right. Yeah. If you do not have the training in recursive algorithms, so usually people are used to the straightforward thinking. Straightforward thinking. Okay? So you work on the whole problem directly. That's the straightforward thinking. Yeah. But for relatively hard problems, the straightforward thinking could be too hard. Too hard. Because when you work on the whole problem, it could be too hard. Yeah. Then, so we want to take a different approach. We want to solve this problem step by step, bit by bit, gradually, slowly, moving up. Yeah. So that approach. Yeah. All right. Yeah. But, so here, actually you can see sometimes we can solve a problem in two different ways. One way, we do not use recursive thinking. Okay? Yeah. We just use our usual non-recursive way. And sometimes we can use recursive way. Yeah. So here I want to do some comparisons. Yeah. So these two different ways, we want to see their advantages and disadvantages. Yeah. So each one has its own advantages, disadvantages. Yeah. All right. And next, then, in this part A, I want to show you the power of recursion. Now, remember, to answer the first question, why we use recursive thinking, the answer is here. The answer is because it is very powerful. So we want to use its power to solve usually hard problems. Hard problems. Yeah. For simple, easy problems, maybe not necessary. Okay? Although you can, if you want, you can, but usually not necessary to use the recursive algorithms. Yeah. But for very hard problem, then you will see if you do not use recursive algorithm, it could be extremely hard. Yeah. It could be, even you may have the situation you couldn't solve it. If you do not use recursive thing, then nobody could solve it. That could happen. Yeah. I will give you one simple example to show you that point. Yeah. If you do not use recursive, you cannot solve it. Yeah. Yeah. All right. Yeah. After you see that example, so you can appreciate this idea. Yeah. Now, let me explain this point. Compare two different ways to solve problem. One non-recursive way, so usually we call it iterative way. So we want to avoid recursion. So this way, we want to avoid recursion. Yeah. So the typical way to avoid recursion, we use iterations, we use for loops, while loops. Yeah. Iterative way. Yeah. Then we can avoid recursion. Okay? Yeah. So we feel very comfortable in this iterative method. Yeah. Then another one, recursive way. Yeah. Now I want to compare advantages, disadvantages, these two methods. Yeah. All right. Iterative way, advantage part, pretty important. It uses less resource, less computing resource. Yeah. Mainly the resource talking about here is memory resource. Memory, yeah. To implement your algorithms, you need to use the memory resource, RAM. Okay, RAM, memory resource. Yeah. Yeah. Storage locations, resource. Yeah. But disadvantage, harder implementation. That's disadvantage. Okay? Yeah. So, yeah. You know, recursive, you need more resource. Yeah. So I will explain why more resource. Okay? Yeah. Yeah. So here, give you the result, more resource. Yeah. Why more? Yeah. We need to look at a little deeper to see that. Yeah. More resource. That's a disadvantage. Okay? Yeah. Then, advantage, easier implementation. Easy. Okay? Easier. It's hard to implement the algorithm. Yeah. When we write the code, the coding is easier. Okay? Coding shorter and easier. Yeah. All right. Yeah. Now let me explain why more resource. Yeah. Because the resource part, we cannot see it. Okay? We cannot see it. Yeah. It happens behind the scene. Yeah. Yeah. Here, I want to explain the internal implementation. Inside computer memory, yeah. How does the high-level programming language implement recursions? Yeah? So high-level programming language should support recursion first, right? Yeah. Yeah. So if you look at the history of the programming languages, yeah, back to early times. At early times, most of the programming languages did not support recursion. Did not support. Yeah. Then, yeah. So the recent modern high-level programming languages all support recursions. Yeah. Because so powerful. Yeah. Yeah. So, yeah. But now we need to understand how does the programming language support recursion. Yeah. The idea actually very simple. Yeah. From there you can see you need a more memory resource. Yeah. All right. Inside main memory, yeah, in order to implement recursion, a special data structure must be used to manage all the computing resources in that data structure. So that data structure you have learned stack data structure. Yeah. Okay. All right. So here, let me explain that stack idea. Okay. Yeah. So this is a typical stack. Yeah. Stack has a main property, right? This data structure has some important property. Yeah. We call first in, last out, right? Last in, first out, right? Yeah. So sometimes people write first in, last out. Or you can also say last in, first out. Okay? Yeah. That's the main property of stack data structure. Now we use this property to manage all the computing resources we need to use in a recursion. All right. All right. Here, I just give you this idea. All right. When we calculate a function, recursive function, so here, suppose here, we want to calculate f of n. Okay? Yeah. All right. Based on the given condition, f of n, when you plug in the value m, the value is not available. Well, the value based on the recursive formula, recursive formula, you need to do recursion to get this n. Okay? Yeah. So then we start our recursion. F of n is not available, then we push it into the stack. Okay? Yeah. So the first step, we push it into the stack. So it's at the bottom. Okay? The first in at the bottom. Yeah. All right. Then f of n, this value relies on f of some smaller numbers, right? Yeah. Yeah. Here, based on your recursive formula. So it could be n minus 1, or, here I just show you the idea, okay? But the f of n minus 1 is still unknown. Then we delay the calculation. How do we delay? Push it into the stack. We hold it, okay? Yeah, yeah, all right. Then we do the recursion. Yeah, keep doing recursion, all right? There you can see you push many unknown numbers into the stack, all right? Then finally, because you cannot do this forever, finally, when you reach the base point, because any recursive formula usually provide base cases, right? F of 1, F of 0 as the base cases, okay? Yeah, yeah. So here, assume F of 0 must be given. Otherwise, you can never find any value. So you have to start from some known value, right? So then, at some point, so here, suppose the 1 unknown, because f of 1 unknown, then you push into it. Then, next one, f of 0, it's known, then you don't need to push it. So you can use it, f of 0. Okay? F of 0 is known. All right, you have it. Then, after that, after you know this f of 0 value, next one, you need to pop up the first unknown value in the stack to do the calculation using the known value. Okay? Then, so f of 1 is known. Okay? After you find the value of f1, then you pop up the next one from the stack. But this time, because you have f of 0, f of 1 both known, so you should be able to calculate f of 2, and so on. Then pop up the next one, and finally you reach the bottom one, because after you reach the bottom one, all the values above are known. Okay? So you can use all those known values, you can find the, your targeting value, f of n. Yeah. That's the recursion idea. Okay? That's the implementation idea of recursion. Yeah. In this way, you can see now we get to the point why we need more resource. Because in order to create the stack in main memory, especially your stack could be deep. Yeah? You push many unknown values, unknown expressions in your stack. So your stack could be very deep. Yeah. Deep, it means you need more memory resource to do the calculation. Yeah. So that's that explains why we use more resource. Okay? Yeah. So it's not free. Yeah. We know usually based on our real experience, the valuable stuff usually not free, right? Yeah. Recursion valuable. Yeah. So this recursive algorithm, very extremely valuable, it's not free. The price you pay, yeah, this deep stack. Yeah. It could be a deep stack. Yeah? Yeah. So later we will talk about this deep stack problem. When your stack going very deep, think about sometimes your program could terminate due to the lack of the enough memory. You run out of memory. You run out of memory. So usually, there is a special word for it. So people call it stack overflow. Your stack, this overflow. Okay? Oh, yeah, because the quantity, your memory has a limited amount, right? Limited amount. But even if you use your whole memory space, still not enough to store that big stack. So you get a stack overflow problem. Uh-huh.
You said that in memory, it's the data type or the data structure that is used as a stack.
Uh-huh.
So wouldn't that stack also be used in iteration?
No, iteration, we do not use stack. Okay? Iteration, we just use simple variables, right? The variables could be reused. The last iteration, those variables you just used before recycled. So you go back, you repeat it, but stack you cannot. So you have to hold. Yeah, hold, yeah. That's why iteration implementation, you can save a lot of memory space. Yeah. All right, yeah. So that point later, yeah, in our discussion, we will, talk about that a lot. Yeah. Because this drawback, this big drawback, sometimes could slow down your algorithm significantly. Yeah? Yeah. The more memory used, the slower your algorithm. Yeah. That could happen. Yeah. So that's an important problem. Later, we need to see what's the solution. Yeah? We need to find some smart way. Yeah. So here you can see the smart way. If you use the straightforward way, we want to reduce the size of the stack. Okay? We need to find a way to, make it shorter, not that deep. Yeah. All right. Yeah. All right. So let's move to the problem solving. Okay. Now we want to see the power. Before we see the power, the first thing we want to see the basic idea of recursive algorithms. Yeah. So let's look at this problem 9. Calculate the factorial. Yeah. It's a very easy problem, but we want to use this simple example to help us understand recursion. Yeah. The structure. Yeah. In problem solving, what kind of special structure do we use to derive the recursive formula? Yeah. So we as programmers, or we as problem solvers, the most important step, so when we solve a problem using recursion, most important step is deriving the recursive formula. If you get that recursive formula, then you're done. Yeah. Yeah. Because implementation, we know how to do the implementation if we have the formula. So now let us focus on how to derive a recursive formula. Yeah. Let's look at a question. Given a non-negative integer n, yeah, find its factorial, n factorial. It's a simple example, yeah, but we can use it to understand recursion easily. Okay, all right. First, the method 1. Yeah, method 1, we do not need to use recursion, right? Yeah, it's because we use the iterative way. Okay, yeah. And from the function definition, yeah, we know it's a product of these n consecutive positive integers. Yeah. You can write a for loop to find the answer easily. Yeah. No recursion. Yeah. Yeah. But first thing, if we want to use the recursion to solve this problem, actually, it is not as good as the iterative way. Yeah. So here I can tell you the conclusion. Recursive way, iterative way is better than recursion way here. Yeah. Because for the question so simple, why you need to use more resource to calculate it, right? Yeah. So it's not necessary. Yeah. But you understand here for the education purpose. Yeah. It's not, recursion way better. So we just want to see the process of recursion. Yeah. All right. Then you need a base case, right? Yeah. The base case here, because sometimes we need to start from the 0. Yeah. So here we assume 0 factorial equals 1. Now 0. Can you see the point? Do you feel it is a reasonable assumption? 0 factorial equals 1. Can you see that? Why it's not 0? It is 1. Okay? Can you see that? 0 factorial is defined as 1, not 0. Yeah. All right, I need to explain because it's not quite intuitive, right? It's not quite intuitive. Yeah. Yeah. So here I can use 2 different ways to explain this. Yeah. 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 Because first we need this. Yeah. Yeah. If we make this assumption, then all the formulas are correct. There is no contradiction. Yeah. Otherwise, you may get a contradiction. If you assume 0 factorial equals 0, you may get a contradiction. Okay? Yeah. We will see that. We will see that. All right. Yeah. Now, implementation. Yeah. Yeah. For the iterative method, implementing just one for loop. Yeah. So simple. Yeah. But now we want to focus on the second method. Yeah. Recursive method. Yeah. To understand the basic step. Yeah. How do we apply our recursive thinking here? Yeah. All right. For the recursive thinking, yeah, so the basic idea, yeah. Remember, we don't want to work on the original problem directly. Yeah. We want to work on the relatively easier version of the original problem. Yeah. Yeah. All right. Yeah. So how to get an easier version? Easier version, here we use remember I mentioned some principle before, right? I remember some principle, we learned some principle before, that is the smaller the problem sizes, the easier the problem, right? If we can make the problem sizes smaller, then the problem is easier. Yeah. Use that principle. Yeah. Remember, I explained the principle. That means 90-something% it's true, but not 100% true, because there are exceptions. Yeah. Here we use that 90% something, that part. Okay? Yeah. We reduce the problem size to make it easier. Then we assume we already have the solution for the problem with smaller sizes. Then let's look at how to get a solution for a problem with larger size. Yeah. That idea. Okay? Yeah. All right. Here actually already we use the divide and conquer approach. Yeah. This is the topic of Module 4. Yeah. Module 4, the whole module we study divide and conquer approach. Yeah. But here we need to use this idea. Okay? Yeah. So let's use it first. Yeah. All right. All right. Yeah. So the principle, remember, the problem is easier when the size is smaller. Yeah. All right. So when we want a problem of the current size, current size. Assume that problem of a smaller size has been solved. Yeah. Assume. Yeah. Why we can assume? Because based on recursion, we can assume. Okay? Yeah. Recursion. Yeah. Remember, push the stack. Eventually, we reach the top. The solution of the top one is available. Okay? Yeah. Then we can use that to solve the problem with larger sizes. Yeah. So that's why we can assume the problem of small size has been solved. Yeah. Then we can do recursion. Yeah. All right. Then fix the gap through a recurrence relation. There is a gap. Yeah. But how to make up that gap part? Yeah. We need to fix it. Yeah. Then we get a whole formula. Yeah. All right. So based on this is a general approach. This is general recursive thinking approach. Yeah. Now let me show you how to apply this general process to solve this problem number 9. Yeah. All right. This is our factorial formula. Let's do divide and conquer. Yeah. Now we need to apply divide and conquer approach on this formula. Okay. Then the first step, divide step. Divide it. Okay. All right. When we do divide and conquer, so here let us give a function representation. Capital F of n represent the whole function. Yeah. Because in this way, we can represent this function in different sizes, right? F of 1, 2, 3, 4, different sizes. Yeah. So more convenient. Yeah. Then we do divide. This time we use the simple divide way. We just cut off the last element. Yeah. After this special way, chop off the last operand in this formula, then the remaining part, the problem, the size becomes smaller. The problem size is one size smaller. One size smaller. Okay? Yeah. But we can assume the solution of f of n minus 1 is already available. Yeah. Yeah. We just assume that. Okay? Yeah. Because we don't worry if it's not available later through recursion, we can make it available. Okay? We can make it available sooner or later. Yeah. So that's why when we reach the current problem, it is already available. When we get to the point working on the current problem, it is already available. Okay? Yeah? Yeah. At the beginning, it may not be available. Yeah. Yeah. But sooner or later, it will be available. Yeah. All right. Then the recursive formula is f of n equals f of n minus 1, the problem of previous size. Okay? One size reduction. Yeah. The problem size reduction. But this special reduction is one size reduction. Yeah. This is a commonly used method. One reduction, one size reduction. Yeah. All right. Then bridge the gap part, we apply that n number back. Yeah. One more multiplication on the known solution. Because you assume f of n minus already known. Yeah. So you multiply one more number on the known solution, so you get a solution of the original problem. Okay? Yeah. All right. So that's our view. So here we used divide and conquer recursive thinking to get this view. Yeah. Although it's not necessary. Okay? Yeah. But for our understanding, so we need this simple example. Yeah. All right. And for this formula, so we need to specify the range for our data we require, and must be positive integers. Positive integers. Okay? Yeah. Then factorial, the definition of factorial makes sense, right? Yeah. Otherwise, we don't know what's the definition of factorial, right? Yeah. So all right. Yeah. Then Now, let me answer the previous question, why our assumption that a 0 factorial equals 1 is reasonable assumption. Yeah. It's not a, some random, arbitrary assumption. Okay? We cannot do, arbitrary assumption. Okay? Yeah, because can you assume 0 factorial equals 100? We cannot. Yeah. So that's why we have to make reasonable assumption. Yeah. All right, but here I show you. I try to justify, this special assumption. Yeah. All right, let us look at our recursive formula. Rewrite recursive formula in this version. How about that? Yeah. Yeah. Just it's an equivalent formula, right? Based on the algebra. Equivalent formula. F of n minus 1 equals f of n over n. Yeah. The two formulas are equivalent. Yeah. But if we use this new expression, now you can see. Yeah. Because the right-hand side, we can plug in n equals 1, right? It's legal. N equals 1 is legal at the right-hand side, okay? All right. Let us plug in n equals 1 at the right-hand side. Yeah. F of 1 over 1. F of 1 factorial is 1, no problem, right? 1 factorial, nobody has a problem on that. So 1 over 1 is also 1. But if you look at the left-hand side, it should be f of 0. Is the meaning f of 0 just 0 factorial? Based on our notation, we define f of 0 as the factorial of that parameter number. Here, it corresponds to 0 factorial. Here, okay? Yeah. Now, the equality should hold, right? If you agree this formula is correct, then you have to agree this one also correct. Yeah. All right? So from this point of view, you can see the only reasonable value for 0 factorial is 1, not 0. Okay? Yeah. So that's from the formula point of view. Yeah. But there is another special point of view. Yeah. I may like to, let you know, yeah, to understand why 0 factorial is reasonable. Yeah. All right. Yeah. Let me look at the time. Another way we can see 0 factorial should be 1. Yeah. So let's go back to our experience. Yeah. Yeah. In our programming experience. Okay, all right. So for our programming experience, let me recall the first experience. The first experience, we do summations. When you write a code, you need to do summations frequently, right? Yeah. Think about, here, let me recall. When you write a code to do one particular summation. So what do you usually do? Yeah. When you start, you need to use a variable. Yeah, here let's say some variable. At the beginning, do you need to initialize your sum variable? Yeah? And your initial value usually should be 0, right? Summation. Okay, all right. Then you take for loop, right? Yeah, so here, for example, we do for loop. Okay? Something like that. Okay? All right. Or, no equal. Okay? Less than n. Let's assume n is array size. Okay? There. So, because array, the last element in the array is a of n minus 1, right? Yeah. Because if the array size is n, the last element in the array is a of n minus 1, not a of n. Okay? Yeah. All right. Then, when you do the summation, do you use this way, sum equals sum plus A of I. That's how you typically do a summation, right? Yeah. All right. Here, so this is our first experience. Okay, we need to connect. All right. Yeah. Then we have another experience. We need to connect. All right. Oh, sorry. We have a lot of time. Oh, okay. Yeah, sorry. I watched the wrong place. Yeah. You know, the break time, we have a lot of time. Yeah. Okay. So let me look at my clock. Yeah. Okay. Yeah. So it's not near the break time. Yeah. We have a lot of time. Yeah. Yeah. Sorry. Yeah. I confused. Yeah. All right. Yeah. Next, another experience. We calculate the product of a sequence of numbers. Yeah. How do we do it? Yeah. Here, let's assume we want to calculate product of all the elements in the array. Okay? In array A. Yeah. So when you do that operation, okay, yeah, do you create a new variable? So here, do you create a new variable? Let's say prod. Okay? What is the initial value? You want to calculate product of all the elements in the array. You need to use a special variable, prod variable. What should be a good initial value here for the product? Yeah, 1. Because this 1 has a great property. It multiplies any number, it is still that number. It does not change that number. It keeps that number. So we need that. So that's our initial value. It's 1. This time you can see we cannot use 0, right? Otherwise we get all zeros. So we cannot get 0. Yeah. We have to use this 1 special value, not 0 special value. All right. Next, we implement this for loop. Yeah, maybe semicolon. Yeah, yeah. All right. Yeah, maybe semicolon. Okay. All right. Plus plus. Yeah. Then here, our main formula is prod multiply A of I, right? Yeah. Our main formula inside the for loop. Yeah. All right. Yeah. Now you can see now. This is the right way to do product of sequence of numbers, right? Yeah. Now think about what's the meaning when your array size n equals 0. N0 means you have no data, right? Your data is empty, right? Your array is empty. Can we understand that? You have an empty array. When you have an empty array, you do no product, right? So you get out of the for loop immediately, right? Yeah, because you get out of the for loop immediately. You have nothing. You know data. When you get out of the for loop, what do you have in your product variable? It's initial value, 1, right? Not 0. Yeah. 0 factorial means you do not do any for loop. You do not do any iteration. You get out of the computation immediately, but you keep your initial value. Okay? Your initial value is 1, not 0. Okay? That's the understanding. Okay? Yeah. All right. Then the last thing I want to talk about, the difference between 0 and 1. Yeah. Why 0 and 1 so special here, right? So here in our calculation, so we get an idea, when we do summations, we should use 0 as initial value. When we do product, so how do we call that? Product of a sequence of numbers. Is there any special word for it? Here we have summation. So what's the corresponding word for the, product. I have never seen it. Yeah. Production? No. Yeah. Anyway, yeah. So here you can see the point is, yeah, why we use zero. We use two different initial values for addition and multiplication. Here, the basic point is sum, not sum. So here, zero is the unit of addition. Yeah. 0 is unit of addition. Why you call it 0 unit of addition? Because 0 plus A equals A. Okay? This tells us 0 is the unit of addition. Yeah. 0, then you do addition with any number, you still get that same number. So this special number we call it unit. In math, there is a concept, unit. But unit with respect to addition operation, that similar concept in multiplication. 1 is unit of multiplication. Yeah, because 1 times B equals B, right? Yeah. Now you can see similarity in these two formulas. The unit, then you do this corresponding operation with any number, you are talking about the same number. You do not change it. That's the role of unit. That's the special role of unit. Okay? Yeah, so here. So you understand. There are different roles. Yeah. All right. All right. Yeah. So now we finish discussion of this problem 9. Okay. All right. Yeah. Conclusion. Yeah. Conclusion. Although we do not say this, our second method is better than the first one. We do not say that. Yeah. But we can say it is, although it's not better, but it is an interesting way to solve problem, right? Yeah. It's an interesting way. Yeah. Okay. It is worth considering. Yeah. Yeah. Worth considering. Yeah. Yeah. All right. Yeah. 8.2, power of recursive algorithms. So this time, now, we want to see its power. The most valuable part of a recursive algorithm, the power. Yeah. All right? Yeah. To see its power, here I want to use some interesting problem, puzzle problem. Yeah. But this problem you learned before. Yeah. Not just learned before, I think most of you should have experience in your, in your early times. Yeah, so you did this puzzle before. Okay? Tower of Hanoi problem. Okay? Puzzle problem, Tower of Hanoi problem. All right, so let me describe the problem. Yeah. Here we have stack of disks. Yeah. But the sizes, yeah. So we arrange the sizes of disks in the decreasing order. Okay? The larger disks at bottom, smaller disks on top, yeah, in that decreasing order. Yeah. Then we have 3 pegs, so we can move these disks on any of the 3 pegs. But we need rules. We need special rules here. Yeah. So there are 3 rules you need to follow when you move the disks. Yeah. Yeah. All right. The first rule, only 1 disk can be moved at a time. Okay? Every time when you move this, you can only move one disk. Yeah. Rule number 1. Rule number 2, a disk cannot be placed on top of a smaller disk. Okay? Yeah. Larger disk, yeah. If you have a smaller one here, you cannot put a larger one on top of it. Okay? Yeah. That's not allowed. Yeah. You have to follow. So, yeah. The order of the disk sizes on every peg, it should be always in decreasing order. Okay? Yeah. The second, rule number 2. All right. Rule number 3, yeah. All disks must be stored on a peg except while being moved. What's that? Because you cannot put any disk on the table. Okay? Yeah? In other words, you use the table as your temporary storage locations. No, you are not allowed. Because in that way, you have more rooms to do the manipulations. That's not allowed. Okay? Yeah. Yeah. So you need to always place any disk on one of the 3 pegs. Rule number 3. Yeah. If you follow these 3 rules, then move 3 here, because the number of disks, that number we can change to n disks. 3 is just special case. But usually for kids, the most popular version is the 3-disk version, because it's simple enough, but not too simple. Yeah, still a little challenging. Yeah, yeah. So usually for, most of the kids, people use this 3-disk version as the puzzle problem. Okay, all right. Yeah. Now the goal, you need to move the 3 disks from the first peg to the last peg, that's the destination peg, using these 3 rules to make the legal moves. Now the question, we need to find a solution. We need to how to solve this problem. Okay, all right. Then, now we use our recursive thinking to solve this problem. Yeah. All right. Yeah. Let's look at the solution. Yeah. Do the analysis. Yeah. Now, to solve this problem, now I want to review our problem-solving strategy. Yeah. Yeah. Some strategy we used before. All right. Yeah. All right. So this time n equals 3, right? Yeah. So it's an n equals 3 version. All right. N equals 3 version already pretty challenging. Yeah. Yeah. Not that simple. Okay. Not simple. Yeah. All right. Then recall the strategy we just used. Actually, we used before, and we just used a few minutes ago. To make the problem easier, can we reduce the problem size a little bit? Problem size a little bit, right? Yeah. We know the smaller the problem size, the easier the problem. And when we start, we can work on the simplest cases. Yeah. All right. So let's look at the simplest cases. Can we consider n equals 1 and then 2? 1, so simple, right? Yeah. 1 move, you solve it. Yeah. So it's a trivial case. Yeah. All right. The next one, not slightly harder, 2 disks. 2 disks, still pretty easy, right? Yeah. Yeah. Because we have 3 pegs. You have plenty of places. You can, put the top disk temporary somewhere. Yeah. So, yeah, these 2 cases very easy. Yeah. Yeah. So we can treat. We have solved the problem. Yeah. Let's use the notation. Yeah. Suppose if we use the p function to represent the solution for the problem of size n. Yeah. Yeah. That means here we can say p of 2, the solution is available, right? Yeah. P of 2 solution is available. Yeah. Next question. can we use the P of 2 solution to help us solve the problem P of 3? Because here our goal is P of 3. There is a gap, right? Between 2 and 3, there is a small gap. Now we need to bridge that gap. Then we can find a solution. So that's the idea. That's the recursion idea. Yeah. All right. Thinking. Yeah. All right. Yeah. So here we can assume we already have the solution of size 2. Yeah. And we can see it. Here, it's not just assumption because we can do it. Yeah. We can make it. Yeah. All right. Next, now we consider the recursion case. Now n equals 3. Yeah. All right. Yeah. It's not trivial. Yeah. All right. Now, let's work on it, right? Yeah. Because n equals 3. Yeah. Here, you know, the amount of work is not too much, so we can work on it here. Yeah. All right. Now, let's do the work. Okay? Let's move the disks. Okay? Move disks around. Yeah. All right. Step 0. When we start, step 0. Yeah. That's the current state before we do anything. Yeah. All right. Step 0. Next step. All right. Move the top disk. You need to keep in your mind those 3 rules. Okay? Yeah. So never violate any of the 3 rules. Yeah. The first move the top disk. You can only move the top disk. Okay? All right. Yeah. Let's move it to peg 3. Okay. Peg 3. Yeah. You may ask me why peg 3. Yeah. So yeah, because when people do experiments, if they move to peg 2 and then later they it's better to move it to peg 3. So now, because after some experiments, when we do an adjustment, we know it's better to use peg 3 as our temporary peg at the beginning. Okay? All right. Yeah. Peg 3. Then, step 2, then we can move the middle disk in peg 2. Yeah. Because the reason we use peg 3 as a temporary peg, because we want to place the middle disk in peg 2, on peg 2. Yeah, that's the reason. All right. After that, then we want to move smallest disk back to peg 2, following the rules. See, we do not violate any rule here. Okay, all right. Now, because peg 3 is empty, can we move the largest disk onto peg 3? Yes, we can. Yeah, yeah. But here you can see this middle peg, you can see we just did P of 2 solutions, right? Yeah. We just did P of 2 solutions. Okay? Yeah. All right. Then, the gap part. Yeah. We just apply our P of 2 solutions. Yeah. Now we need to work on the gap part. What's the gap part? We need to move the bottom disk. Yeah. Bottom disk to our destination peg. And fortunately, this time, our destination peg is empty. So we can move our largest disk to peg 3. Okay, another move. After that, after step number 4, can you see we need to move these 2 disks back to peg 3? You can see that's another round you need to apply P of 2 solutions, right? Because moving 2 disks, that's P of 2 solution. Yeah. All right, so let's apply that P of 2 again. Yeah. So this time, the smallest, move number 5, move the smallest disk to peg 1. Yeah. Because next you can move the middle disk to peg 3. Then the last move, move number 7, you move the smallest disk back to peg 3. So you solve the whole puzzle problem. Okay? Yeah? Solve the. Here you can see you need 7 steps to find a solution. You need to make 7 moves to get a final solution. Yeah. All right. That's our experiment. Yeah. But our goal, we want to solve P of n. This is our goal. Okay? All right. Yeah. When we write a program, we need to solve this P of n problem. Now, the next question, can we generalize our solution from P of 3 to P of n? Yeah. So that's the next question. Yeah. All right. All right. To generalize, yeah. So here. Yeah. First you can see, yeah, to solve P of n, if someone asks you to solve this P of n directly, is it very hard? Given any disk number, it could be 100. If you need to move 100 disks, you need to specify all the moves for 100 disks. Too hard, right? Yeah. Yeah. You will get lost. Okay. So that is very hard. Yeah. Now you can see the recursive way actually is an easier way for us to find a solution. Yeah. Otherwise, we don't know how to solve it. Okay? But if we use the recursive way, now we can see it's doable. Yeah? By recursion, it's doable. Yeah. All right. Let's look at the implementation here. Yeah. 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 Here, when we use the recursion way, when we work on the current problem size n, we can assume P of n minus 1 is already available. The solution of the previous problem size is already available. Yeah. That's the important step in the recursion. Yeah. Because in that way, if we only do the gap part, that's not that hard, right? Yeah. Think about it. You have the solution moving n minus 1 disks from one peg to any of the destination pegs. Yeah. Then you do the gap part, that means the bottom disk. Moving the bottom disk to the destination peg, that's so easy. Okay? Yeah? All right. So now let's look at the general solution. General solution here. All right. All right. Two peg, that's the destination peg. From peg, beginning peg, then the middle one, temporary peg. Okay? Temporary peg. Yeah. All right. Now, here, let's imagine our stack. It's a size n problem. Yeah. So we imagine, so here, because it's hard to draw n stack picture, yeah, so I still use the 3 stack picture. Yeah. All right. Our goal, we need to move all the n disks to the destination peg. Okay? All right. To do that, yeah, let's do this. Let's apply our n minus 1 solution first. Yeah. So this is the n minus 1 solution. Let us apply this n minus 1, P of n minus 1, and make temporary peg as the destination peg. When we apply P of n minus 1, we use the temporary peg as the destination peg. That's okay, right? Yeah. That's okay. Okay. Then the gap part. Yeah. Fixing the gap part. Yeah, okay, good. Yeah. We're near the break time. Okay. Yeah. All right, so we finished this slide, so we're at a break. Yeah. All right, the gap part, then move the bottom disk, okay? Yeah, the bottom, yeah, so here, let me just draw it, okay? The bottom disk, then apply moving the N-1 disk back to the destination peg. See? Yeah? Yeah. So here, what do you see? You can see the step. The first big step, we apply P of N-1. Okay? Yeah. The second step, move the bottom disk Step 3, then we apply P of N, another one with different destination peg. Okay? In this way, you can see we find a solution of this P of N. Okay? After these 3 steps. Okay? But step 1 and step 3, both recursion step. Recursion step. Okay? All right. All right, yeah. So let you take a break. So when you come back at 7, so we complete the remaining part. Yeah. Probably we may have some time, so we can start part B. Yeah. Because the remaining part, we do not have much left for part A. So I can start part B a little bit. Yeah. All right.